Hello, friends, and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are in this wide world, this little pocket of calm was made just for you, a quiet space where science and wonder can sit side by side, gently carrying you towards sleep. Tonight, we're going to drift back millions of years to one of Earth's strangest and most mysterious chapters, a time when life itself transformed in a way so sudden, so strange, it still puzzles scientists today. For billions of years before this period, life on our planet had been still, quiet, almost invisible. The seas were filled with nothing more than drifting microbes, mats of bacteria, and jelly like bodies that barely left a trace behind. And then, as if Earth itself had woken from a dream, everything changed. Monsters unlike anything before suddenly filled the seas. Spiked worms bristled with armor. Five-eyed hunters scanned the darkness of the ocean floor. Predators with circular, saw-like mouths tore into their prey. In this brief window of time, known as the Cambrian Explosion, nearly every major group of animals that exists today was born. The blueprint of every fish, every insect, every mammal, and every human being alive today can be traced back to this strange silent sea 500 million years ago. It was as though the planet itself had thrown open the gates of possibility, letting evolution run wild in the greatest experiment life would ever stage. But why then? Why, after billions of years of stillness, did the seas suddenly boil with life? Was it a sudden shift in climate, or perhaps a new genetic key that unlocked endless possibilities? Tonight, we'll drift into those alien oceans together to uncover the experiments of evolution. We'll meet the predators and the survivors, the forgotten forms that flourished for a moment and disappeared, and wonder at how this ancient explosion still echoes inside our very DNA today. But before we continue, if you enjoy journeys like this, soft, soothing, and quietly filled with wonder, I'd love it if you gave this video a gentle like and maybe tapped subscribe. It helps more curious minds like us find their way here and lets the algorithm know that sleep and science belong together. And if you feel comfortable sharing, I'd love to know in the comments, where are you tuning in from tonight and what time is it there? It's always a joy to see how far across the world these quiet stories travel. Now take a deep breath, let your shoulders soften, and together let's journey into the Cambrian Explosion, evolution's first great experiment. For most of Earth's history, life was quiet. The oceans stretched wide and endless, their surfaces stirred only by winds and tides. Yet beneath them, for billions of years, there was little movement beyond drifting clouds of microbes. These single-celled organisms were the planet's first tenants, and for an unimaginable stretch of time, they held the stage alone. They clustered into colonies, forming mats on the seafloor that looked like thin carpets of slime. They floated freely, catching sunlight or feeding on the faint chemistry around volcanic vents. Though they were invisible to the eye, they altered the very air and water. By releasing oxygen, they slowly transformed the planet into a place capable of sustaining more complex forms of life. The world was alive, but it was not yet busy. There were no swarms of fish, no forests of coral, no creatures chasing one another in the shallows. For nearly 4 billion years, this was the state of things, a long stillness broken only by tiny pulses of microbial activity. To walk along a shoreline, then, if one could have, would have been to see empty beaches and barren tides, waves rolling onto land that held nothing more than simple algae. Eventually, something new began to appear. In the last moments before the Cambrian period dawned, the seas harbored strange organisms that scientists call the Ediacarans. These were soft-bodied creatures that defy easy comparison to anything alive today. Some looked like fronds pressed flat into the sediment, others resembled quilted discs, and a few stretched into shapes like ribbed pillows. Their fossils are impressions rather than skeletons, delicate outlines pressed into stone that hint at bodies without bones, shells, or even clear heads. They had no eyes, no jaws, no recognizable organs, and yet they were larger than the microbes that had dominated before, reaching lengths of several inches, sometimes even a foot or more. The Ediacaran organisms were Earth's first attempt at building bodies on a larger scale, but they remain puzzling. Some scientists believe they were early animals, primitive forerunners of forms that would later thrive. Others argue they may have been a separate branch of life altogether, experiments that left no descendants. Their fossils do not tell us clearly how they fed or how they reproduced. Some may have absorbed nutrients directly through their skins, others may have grazed gently across microbial mats. Whatever their strategies, they filled the oceans with a quiet strangeness, a community of beings that slipped into existence and then faded away. For a time, these soft-bodied forms dominated shallow seas across the globe. They covered seafloors in patterns that looked almost like gardens, still and silent. They lived in a world with no predators, a world where defenses were unnecessary, where life unfolded at the slow pace of growth and decay. And yet, even with this step forward, evolution seemed hesitant. Complexity emerged only in hints, not in leaps. For tens of millions of years, the pace of change was sluggish, as though the planet were gathering its strength before unleashing something greater. Why did life linger in this state for so long? That question remains one of science's great mysteries. Some researchers suggest that oxygen levels, while rising, were still too low to support the energy demands of active, mobile creatures. Others point to the chemistry of the oceans, which may not yet have been favorable for building shells or skeletons. It is also possible that genetic toolkits, the deep codes that allow for the development of complex body plans, had not yet been assembled. Whatever the reason, the Ediacaran seas remained a subdued theater, filled with creatures that were curious and strange, but quiet and passive. The fossil record shows that toward the end of this era, many of these organisms vanished. Their disappearance left room for something entirely new, something that would not just occupy space but transform it. The stage was cleared for the first predators and prey, for bodies armed with claws and eyes, for movement and struggle and innovation. The long silence of microbial mats and quilted forms would give way to sudden bursts of activity. The oceans, once hushed and still, were about to become crowded with experiments that reshaped the history of life forever. And so, as the Ediacaran world slipped away, conditions were gathering quietly in the background. Oxygen levels continued to climb. Nutrients washed from the continents into shallow seas. The Earth itself was preparing the canvas for an evolutionary event, unlike anything that had come before. What followed would not be gentle, and it would not be slow. The Cambrian period was about to begin. As the quiet seas of the Ediacaran faded, the planet itself was shifting in ways that would change everything. The Earth was not still, even if life had seemed so. Beneath the oceans, heat moved continents, pushed up mountains, and split apart crusts of rock. Above the waves, air and water carried subtle changes that would soon ripple into every living thing. For a long while, these shifts were unnoticed, yet together they built the conditions that would set the stage for life's sudden eruption. One of the most important changes was the rise of oxygen in the oceans. For billions of years, oxygen levels had been low, barely enough to support large or active creatures. But during this time, the balance began to tilt. Microscopic algae, drifting in the sunlight near the surface, released oxygen with every breath. Stromatolites, ancient colonies of microbes, continued their slow work of reshaping the chemistry of air and sea. Slowly, Molecule by molecule, oxygen accumulated in the water. Higher oxygen meant that energy could flow more freely through living bodies. Muscles could pull harder, nerves could spark more rapidly, tissues could grow thicker and more complex. With more oxygen, animals could build larger forms, sustain activity for longer, and support organs that required greater energy. What had once been impossible was suddenly within reach, and this shift alone opened possibilities that had been closed for almost 4 billion years. At the same time, the oceans were being fed in new ways. As mountains rose and continents shifted, rain and wind eroded fresh rock. Rivers carried nutrients into the sea, minerals rich in phosphorus and nitrogen that fertilized the waters. These nutrients fueled the growth of algae and plankton, small organisms that bloomed in great numbers. Their presence created food at the very base of the food web, offering energy for creatures that grazed, filtered, or hunted. Sediment washed into shallow seas as well, softening the seafloor and creating layers of mud where burrowers could dig, hide, and search for nourishment. The shifting of the continents also played its part. During this time, the arrangement of land and sea was far different from today. Large land masses broke apart into smaller pieces, and the movement of tectonic plates created vast stretches of shallow water along continental edges. These shallow seas were unlike the deep open ocean. Sunlight could reach the seafloor, warming it and encouraging growth. Nutrients carried by rivers collected there, instead of being lost to the abyss. Shallow seas became laboratories for experimentation, places where new forms of life could test their survival. It was within these shallow, oxygen-rich, nutrient-filled environments that the stage for the Cambrian Explosion was set. Here, life had both the energy and the raw materials it needed to explore new shapes and strategies. The seafloors became busy places, not yet filled with predators but ripe with potential. The conditions were finally in place for bodies to grow larger, for skeletons to harden, for eyes to develop, and for the first true ecosystems to take form. And yet, even as these changes unfolded, they did not act alone. The Earth's climate was stable, the oceans warm, the poles free of ice. This stability may have allowed small shifts in chemistry and biology to build without interruption, each new layer adding to the momentum. For millions of years, the ingredients were mixing, unseen but powerful, preparing the world for what was about to come. From quiet oxygenation to nutrient surges, from the grinding of tectonic plates to the creation of shallow continental shelves, the planet was aligning itself in extraordinary ways. The stage was being prepared for the sudden emergence of bodies unlike any seen before. Strange creatures would soon rise in these waters, feeding, fighting, and filling the oceans with motion and color. The long stillness of Earth's early seas was ending, and the next chapter was about to unfold. Among the first creatures to rise in the Cambrian seas was one so strange that even its fossil remains seemed like a trick of the imagination. Small enough to fit on the tip of a finger, yet bristling with an appearance that defied sense, it was given a name that reflected its dreamlike absurdity: Hallucigenia. Hallucigenia was a worm-like animal, delicate in size yet fierce in appearance. Its body was thin and soft, no longer than a few centimeters, but from its back jutted long, sharp spines. Each spine was rigid, tapering to a needle-like point, and arranged in a row that made the animal look as though it carried a row of jagged weapons wherever it went. These spines may have glistened under the light, filtering into the shallow Cambrian seas, standing out against the dark sediment below. To a predator seeking an easy meal, the message was clear. This was not a creature to swallow without risk. Along its underside were tiny stilt-like legs, each tipped with a soft claw-like end. The legs gave it a peculiar gait, as if it were walking on flexible stilts, stepping slowly across the sea floor. With its tall spines and its delicate legs, Hallucigenia looked less like an animal than like an artist's sketch of something imagined in a dream. It is no surprise that when scientists first uncovered its fossils, they struggled to decide which way was up. For years, reconstructions of Hallucigenia showed it inverted. The legs were mistaken for spines, and the spines were thought to be legs. Diagrams presented it walking on stiff spikes, a row of soft appendages waving above its back like balloons on strings. To early researchers, even this upside down version was baffling, but it seemed possible. Only later, with new fossils and careful comparisons, did scientists realize the truth. The spines were defensive, rising from its back, and the legs belonged on the ground. The creature that had puzzled paleontologists for decades was stranger still, but at last its true form came into focus. Even with its anatomy corrected, Hallucigenia retains an uncanny air. Its body is long and narrow, with a head so small and indistinct that it seems to vanish into its form. Early interpretations once pictured it headless, with food passing straight through. Later studies revealed a tiny head at one end, bearing a circular mouth and simple sensory organs. The mouth itself, lined with small structures, hints at a way of feeding that remains debated. Some believe Hallucigenia sucked in organic matter from the seafloor. Others suggest it grazed on microbial mats that still clung to patches of sediment. Whatever its diet, it did not need to be fast or fierce. Its spines did the work of protection, and its legs carried it carefully through a crowded world. The spines may have served more than defense. Some researchers propose they helped anchor the body, preventing the worm from sinking into soft mud. Others think they may have made Hallucigenia look larger and more difficult to attack. To a small predator of the Cambrian seas, a creature bristling with sharp extensions was a dangerous prospect. Evolution often favors the simplest solutions, and for Hallucigenia, spines may have been enough to ensure survival. Its strangeness is part of why Hallucigenia has become one of the icons of the Cambrian. It captures the sense that this was a time of bold experimentation, when body plans stretched the imagination. There were no fixed rules, no long history of successful designs. Evolution was testing possibilities, throwing out shapes and features like drafts in a sketchbook. Some would endure, refined and reshaped into the animals we know today. Others, like Hallucigenia, would leave only fossils, reminders of a world that once was. Modern studies reveal that Hallucigenia was not entirely alone in its lineage. It belonged to a group of animals called Lobopodians, relatives of the velvet worms that crawl today in tropical forests. Those modern creatures, with their stubby legs and soft bodies, give us a faint glimpse of what Hallucigenia may once have been like in motion. Yet the velvet worms lack the towering spines that made their ancestors so remarkable. The connection ties the surreal Cambrian world to the present, showing how even the strangest forms can echo across time. Hallucigenia's fossils, flattened into stone, continue to puzzle and inspire. They remind us that the Cambrian explosion was not only a story of success and survival, but also of daring experiments that challenged every boundary of form. The tiny worm with its jagged weapons walked softly through its seas, an alien presence in a world that was only beginning to awaken, and around it, in those same waters, even stranger shapes were waiting to be revealed. In the same seas where Hallucigenia crept with its spines raised like jagged shields, another creature moved with a very different design. It was neither armored nor bristling, yet it carried an appearance so surreal that the first scientists to study it reportedly laughed aloud when they saw its reconstruction. This was Opabinia, a hunter unlike anything that had come before, and unlike anything that has ever followed. Opabinia was a small animal, its body no more than a few inches long, yet its features seemed stitched together from separate blueprints. Along its back ran a series of soft lobes that allowed it to swim in gentle undulations, gliding just above the seafloor. Its tail split into delicate flaps, steering it like a tiny rudder. These details might have made it seem graceful, but then came the features that turned it into one of the most alien looking animals in the entire fossil record. At the front of its body extended a long, flexible appendage, almost like a trunk or a proboscis. This strange organ stretched out and bent freely, ending in a claw like structure that could grasp and hold. It seems to have been Opabinia's primary tool for survival, reaching into cracks, tugging at prey, or sweeping food into its small circular mouth that faced backward under its head. The trunk gave it a reach that few Cambrian creatures possessed, turning the animal into a precise hunter of hidden or slow moving prey. But even stranger than the trunk were the eyes. Not one or two, but five separate eyes sat atop its head. Arranged like small turrets, they faced in different directions, giving Opabinia a wide field of view. Some were higher, others lower, together forming a crown of vision that allowed it to scan the world around it. With five eyes, Opabinia could look ahead, above, and to the sides all at once, a tremendous advantage in a world where danger and opportunity appeared suddenly. The image of this creature, gliding low over the sediment with its proboscis extended and its five eyes glinting, is unlike anything seen in today's oceans. Scientists have debated what Opabinia ate and how it used its unusual equipment. One idea suggests that the trunk allowed it to probe into the mud of the seafloor, pulling out small invertebrates or scraps of organic material. Another proposes that it used the claw to snatch soft-bodied prey and lift it directly into its mouth. Fossil evidence hints that it may have been a scavenger as well as a hunter, taking advantage of whatever food lay unprotected. Its five eyes would have helped it detect movement, while the trunk reached into spaces where other creatures could not. In many ways, Opabinia represents the experimental spirit of the Cambrian Explosion. Its body plan has no direct parallel among living animals. It was not an arthropod, though it shared traits with them. It was not a worm, though its long shape suggested something similar. It seems to have belonged to an early branch near the roots of arthropods, perhaps related to the ancestors of insects, crabs, and spiders, but distant enough to stand apart. When paleontologists try to place it within the tree of life, they find themselves sketching lines that do not connect smoothly, as if this creature were a side note, a one-time attempt by evolution to test a new idea. The very strangeness of Opabinia is what makes it memorable. Unlike Hallucigenia, whose lineage connects faintly to velvet worms, Opabinia left no clear descendants. Its design vanished when the Cambrian ended, leaving only fossils pressed into shale. To study them is to glimpse a world where rules were still fluid, where bodies could take on almost any shape. It is a reminder that the forms we know today, the fish and mammals and birds, are only the survivors of countless experiments that once filled the seas. Opabinia's five eyes, staring in all directions, seem to look out at us across 500 million years, inviting wonder at the strangeness of life's possibilities. And while this peculiar hunter slipped quietly out of history, others in its waters were rising to far greater power. In those same oceans, an animal much larger and fiercer was beginning to dominate, a predator whose very name means unusual shrimp, and whose presence would forever change the balance of the Cambrian seas. In the same seas where tiny worms crept along the mud and five-eyed hunters reached with flexible trunks, a far larger shape moved with quiet power. It was sleek, segmented, and graceful in the water, yet it carried an arsenal that made it the terror of its age. This was Anomalocaris, a creature so unusual that its name means strange shrimp, and for a long time scientists believed its fossils were the remains of several different animals. Only later did the pieces fit together to reveal a single predator, one that stood at the very top of Cambrian food chains. Anomalocaris was enormous by the standards of its time. While most Cambrian animals measured no more than a few inches, this hunter stretched close to 3 feet, perhaps even longer in some species. In a world where most creatures fit in the palm of a hand, Anomalocaris would have loomed like a giant. Its long, flexible body undulated through the water with the help of lateral flaps, rippling movements that carried it swiftly forward. At the rear, a fan-like tail acted as a rudder, giving it control as it glided across the seafloor in search of prey. What made Anomalocaris truly fearsome were the weapons at its front. Extending from either side of its head were a pair of spiny appendages, curved and jointed, able to snap shut like grasping claws. These appendages were perfect tools for snaring soft-bodied animals, pulling them inward toward its mouth. The mouth itself was among the strangest features of all, a circular structure lined with overlapping plates that formed a ring of jagged edges. When it closed, the plates met like the blades of a serrated trap, grinding whatever was caught within. This bizarre arrangement, unlike the jaws of any animal today, made Anomalocaris one of the first large predators capable of crushing and tearing through its prey. Fossil evidence shows that trilobites, with their armored shells and compound eyes, were frequent victims. Many trilobite fossils have been found with damaged exoskeletons, the kind of injuries consistent with the bite of Anomalocaris. The predator's serrated mouth may have struggled with the hardest shells, but it could still inflict deep cracks and pry open defenses that smaller animals could not. For softer prey, there would have been no escape. A sweep of the appendages, a pull toward the circular mouth, and the victim was gone. The rise of Anomalocaris marked a turning point in the story of life. Before its arrival, most animals survived by grazing, filtering, or slowly scavenging. Predation existed, but rarely on such a scale. Anomalocaris brought a new level of intensity to the oceans. It hunted actively, pursued its meals, and used both speed and strength to dominate. In doing so, it forced every other creature to adapt. Trilobites developed thicker armor and more agile movements. Burrowers dug deeper into the sediment for safety. Defenses multiplied, and the arms race that defined much of the Cambrian was pushed into overdrive. What makes Anomalocaris so remarkable is not only its size or its weapons, but also what it represents: the beginning of true predator dominance. From this point forward, ecosystems would always have a top hunter, a creature whose presence shaped the behavior and evolution of everything around it. The Cambrian seas, once filled only with grazers and scavengers, now held a new hierarchy. With Anomalocaris swimming above, survival demanded innovation. The fossils of Anomalocaris are found in deposits like the Burgess Shale, where its soft tissues were preserved in extraordinary detail. These fossils show the fine lines of its swimming flaps, the delicate spines of its grasping arms, and the full outline of its strange, circular mouth. Each detail paints a picture of a predator that was not only efficient, but also elegant in form. It was the prototype of a new way of life, a design that combined power with motion in a way no creature had achieved before. And though Anomalocaris itself would one day vanish, its legacy continued. The pattern of large, active predators shaping entire ecosystems was set here in these Cambrian seas. The balance between hunter and hunted would become one of the central forces of evolution, driving the rise of armor, speed, eyes, and complex behaviors. Anomalocaris was the beginning of that story, the first to wear the crown of apex predator. In the waters where it swam, Trilobites and other creatures scuttled and fled, while spined worms and soft-bodied forms searched for refuge. The oceans were no longer a quiet stage of drifting experiments. They had become a battlefield filled with movement, pursuit, and survival. And at the center of it all, Anomalocaris glided with silent strength, the undisputed ruler of its world, while beneath it, one of the most enduring survivors of the Cambrian Age, was beginning its own remarkable story. While Anomalocaris prowled the Cambrian seas with its spined appendages and circular mouth, other creatures were finding ways to withstand its power. Among them were animals that would come to define not just the Cambrian period, but much of early animal life for hundreds of millions of years. These were the Trilobites, the armored survivors, whose fossils now line museum cases and fill stone slabs around the world. Trilobites were among the first animals to master the art of armor. Their bodies were encased in hard exoskeletons made of calcium carbonate, segmented like plates of living stone. This armor gave them a resilience that few Cambrian creatures could match. It also preserved them in astonishing numbers, leaving behind a fossil record so abundant that trilobites have become symbols of deep time itself. When one looks upon a trilobite fossil, the shape of its armor is as sharp and intricate as it was 500 million years ago. The armor was not a single shield, but a series of articulated sections. This gave trilobites both strength and flexibility. They could scuttle across the seafloor with quick, coordinated movements, each segment moving in harmony. When threatened, many species had the ability to roll themselves into tight balls, tucking their vulnerable undersides safely within their shells. This defensive posture, so similar to the pillbugs we see today, was a response to the new pressures of predation. Where Anomalocaris brought the bite, trilobites brought the shield. But their defenses were only part of their success. Trilobites also carried one of the most advanced visual systems of their time. Their compound eyes were made of calcite, the same mineral as their armor, shaped into hundreds of tiny lenses. Each lens captured a portion of the world around them, combining into a mosaic of vision that allowed them to detect movement and light with remarkable accuracy. In some species, the eyes curved around the sides of their heads, granting nearly panoramic views of their surroundings. In a world of sudden attacks, to see well was to live longer, and trilobite eyes were among the first complex visual organs on Earth. The sheer diversity of trilobites is staggering. They were not a single type of creature, but an entire class of animals with thousands of species. Some were small, no larger than a fingernail, creeping slowly through the mud. Others grew to lengths of a foot or more, prowling the ocean floor with greater authority. Some were streamlined swimmers, while others hugged the sediment in flat, broad shapes. Their adaptations filled nearly every niche available in the Cambrian seas. They grazed on algae, sifted through sediment for food, scavenged, and in some cases may even have been small predators themselves. This diversity made trilobites one of the dominant groups of the Paleozoic era. For nearly 300 million years, they thrived, surviving not just in the Cambrian, but across multiple ages that followed. Their persistence speaks to the strength of their design, a combination of armor, vision, and adaptability that allowed them to flourish while other experimental body plans vanished. Their fossils are found on every continent, reminders that these creatures once filled the oceans from pole to pole. For paleontologists, trilobites offer more than sheer numbers. Their well-preserved exoskeletons record fine details of growth, molting, and even behavior. Fossils show evidence of trilobites walking in lines across the seafloor, perhaps traveling together in groups. Some species display intricate spines and horns, suggesting elaborate defenses or even displays. Each new fossil bed reveals patterns that deepen the story of how these armored beings lived. The presence of trilobites reshaped Cambrian ecosystems. Their abundance made them central to food webs, both as prey for larger predators and as consumers of smaller organisms. Their compound eyes pushed the evolution of sight forward, creating pressure for other animals to evolve better camouflage or swifter movements. Their armor sparked an arms race, inspiring sharper claws and stronger bites in the creatures that hunted them. In many ways, trilobites were not just survivors of the Cambrian explosion, they were participants in its acceleration, driving others to adapt in turn. Even as they scuttled beneath the shadow of Anomalocaris, trilobites endured. Their segmented bodies and crystalline eyes left a legacy written in stone, one that still speaks of their resilience and dominance. And while they filled the seas in their millions, other creatures were finding their own ways to face the threats of the age, carrying bodies covered in bristles and spines that turned them into walking fortresses. As trilobites marched across the Cambrian seafloor with their crystal eyes and jointed armor, other creatures developed very different strategies to endure the rising tide of predation. Among these was Wiwaxia, a small, soft-bodied animal that at first glance might have seemed unremarkable, yet a closer look revealed one of the most curious suits of natural armor in Earth's history. Bristling with spines and covered in scales, Wiwaxia was a creature designed to deter, confuse, and frustrate the hungry jaws of the predators that prowled its world. Wiwaxia's body was no larger than a thumb, oval in shape and soft at its core. Its fragile form might have made it an easy target, but nature had provided it with protection. Across its back and sides lay rows of tiny overlapping scales, known as sclerites, that formed a shield around the vulnerable body beneath. These scales gave it a texture that may have shimmered faintly in the dim light of the Cambrian seas, like a mosaic of hard plates pressed into living tissue. The most striking feature of Wiwaxia, however, was the array of long, sharp spines rising from its back. These spines stretched outward like a crown of thorns, curving slightly and pointing in different directions. Any predator that attempted to bite into Wiwaxia would have found its mouth filled with stabbing defenses instead of soft flesh. Even Anomalocaris, with its powerful grasping appendages and serrated mouth, may have thought twice before attacking such a prickly meal. The spines did not make Wiwaxia invincible, but they surely increased its chances of survival in a world where speed and strength often decided fate. Beneath its armor, Wiwaxia crept slowly across the sediment, feeding on whatever food it could find. Paleontologists believe it used a rasping organ similar to the radula found in modern mollusks to scrape algae or microbial mats from the seafloor. This connection places Wiwaxia close to the ancestry of mollusks, the group that would later give rise to snails, clams, squids, and octopuses. In Wiwaxia, we glimpse the early experiments that shaped one of the most diverse branches of animal life. Though it lacked the elegance of a swimming squid or the intelligence of an octopus, its simple grazing lifestyle shows how even modest creatures can leave echoes that stretch into the present. The defensive adaptations of Wiwaxia reveal the intensity of the Cambrian arms race. With predators like Anomalocaris hunting actively, prey animals needed strategies beyond passivity. Some grew armor that encased their entire bodies, like trilobites. Others relied on speed or burrowing. Wiwaxia's approach was deterrence, presenting a body so bristling with obstacles that any attacker risked injury or wasted effort. It was not about defeating the predator, but about persuading it to move on to easier prey. In evolutionary terms, survival often belongs not to the strongest, but to the one most difficult to kill. Fossil beds, such as the Burgess Shale, preserve exquisite impressions of Wiwaxia, showing the details of its scales and spines in fine relief. These fossils capture the animal frozen in its quiet life, creeping along the mud, its armor arranged like a living fortress. They remind us that defense has always been as creative a force as attack. For every predator innovation, prey developed counters, and Wiwaxia was among the earliest examples of this constant exchange. The sight of such a creature in its time must have been uncanny. Imagine the seafloor dotted with small, bristling ovals, each one creeping slowly, their spines shifting slightly with the water's movement. They were not fast, nor particularly complex, yet their strange silhouettes would have made the Cambrian landscape appear alive, with odd defenses. In a way, Wiwaxia represents the quieter side of the explosion, the animals that did not dominate by force, but by persistence, adapting enough to remain in the game of survival. As predators grew larger and more sophisticated, creatures like Wiwaxia carried forward the lesson that survival did not always belong to size or strength, but to creativity in design. And around these spined grazers, the oceans continued to fill with creatures whose lives were shaped by the balance between hunter and hunted, a balance that pushed evolution into ever new directions. The Cambrian seas were no longer a quiet place of drifting bodies and simple grazers. With creatures like Anomalocaris gliding through the water and others like Wiwaxia bristling with defensive spines, a new kind of struggle began to shape evolution. For the first time in Earth's history, the relationship between predator and prey became the dominant force driving innovation. This was the Cambrian arms race, a spiral of survival in which every advantage demanded a counter, and every counter created new challenges. Predation introduced an urgency that had not existed before. In earlier ages, survival had been mostly about finding enough sunlight or nutrients, or simply clinging to existence in stable but limited forms. Now, life itself was being hunted. To escape becoming a meal, animals had to develop defenses, and predators in turn had to find new ways to overcome them. The result was an explosion of body plans, behaviors, and strategies, each one testing the boundaries of what evolution could create. One of the most direct responses was armor. Trilobites thickened their exoskeletons, adding plates that could resist bites. Some grew elaborate spines projecting from their sides, making them harder to grasp. Others learned to roll into tight, protective balls, sealing their soft parts within shells of mineralized armor. The harder the prey became to attack, the sharper and stronger the predator's tools had to grow. It was a cycle that never stood still. Not all defenses were about hardness. Many creatures relied on speed. Small swimmers developed flexible bodies and fin-like flaps to dart quickly away from danger. Even those that could not match the raw power of Anomalocaris could sometimes survive by outmaneuvering it, turning sharply or diving into crevices before the predator's claws could snap shut. Movement became as much a weapon as teeth or armor, and the oceans filled with animals that could flee as well as they could feed. Others looked downward for safety. The soft mud and sediment of the Cambrian seafloor became a refuge as animals learned to burrow. Some dug shallow grooves to hide their bodies, leaving only faint traces of movement above. Others carved deeper tunnels, disappearing into the earth itself, safe from the eyes and claws above. This digging reshaped the seafloor, churning the once stable microbial mats and replacing them with shifting landscapes of burrows and mounds. What had been flat plains of life was transformed into a complex environment of shelters and hidden worlds. Spines and bristles also multiplied in remarkable ways. Wiwaxia carried its crown of defensive spikes, but it was not alone. Many small creatures sprouted sharp projections, each one a warning to predators that an easy meal was not guaranteed. Some spines may have been venomous, others simply painful or awkward to swallow. In a world where every bite carried risk, predators became more cautious, and prey with spines gained precious moments to escape. Perhaps most subtle of all was the rise of camouflage. Soft-bodied animals began to take on patterns that blended with the seafloor, disguising themselves against sediment and stone. Some may have mimicked the texture of algae mats, lying unnoticed as danger passed by. Others evolved transparent tissues, fading into the water itself. These quiet strategies were as effective as armor, allowing fragile creatures to survive by vanishing into the background of their environment. The arms race did not favor one side over the other. Instead, it created a spiral of escalation. As defenses grew stronger, predators became faster, sharper, more cunning. As predators improved, prey found new ways to resist or evade them. This constant exchange pushed evolution forward at a pace never seen before. Where once life had lingered in stillness for billions of years, now it raced through possibilities, filling the oceans with diversity and complexity. The Cambrian explosion was not just about strange shapes or sudden appearances, it was about interaction. Every predator's strike created pressure for change, and every prey's defense sparked new adaptations. Out of this tension came eyes that could see, shells that could resist, muscles that could power swift escapes, and patterns that could trick the keenest hunter. Life itself was sculpted by conflict, but also by resilience, each creature carrying the memory of battles written into its body. In these waters, the blueprint for future ecosystems was being drafted. The balance of hunter and hunted, of offense and defense, became the heartbeat of the natural world. And as this battle unfolded, it was sight that emerged as one of the most powerful tools of all, opening a new chapter in the race between predator and prey. In the Cambrian seas, survival often depended on who noticed whom first. A predator that could detect prey from even a short distance away gained a decisive advantage, while prey that could sense a hunter's approach had a chance to flee or hide. Out of this silent struggle emerged one of evolution's most transformative innovations: vision. Before the Cambrian period, life had little need for complex sight. Many organisms sensed light only in the most basic way, distinguishing brightness from darkness, day from night. Some could detect the faint glow of the sunlight filtering through shallow water, enough to orient themselves but not enough to see shapes or movement. In a world where predators were rare and food was gathered slowly, such limited senses were sufficient. But the arms race of the Cambrian demanded more. The seas had become crowded with animals pursuing one another, and in this new environment, the ability to truly see changed everything. The first eyes were simple. They were small clusters of light-sensitive cells that could detect shadows or the direction of light. Even this was useful, for it allowed creatures to move toward food or away from danger with more accuracy than before. But over time, natural selection refined these clusters into organs capable of greater detail. Lenses began to form, bending light into clearer images. Compound structures appeared, dividing vision into many small units that together created a mosaic view of the world. Slowly, the oceans filled with animals that could not only sense light, but perceive shapes, edges, and movement. Among the creatures that perfected this new sense were trilobites. Their compound eyes are among the earliest examples of advanced vision in the fossil record, and they remain some of the best preserved. Each trilobite eye was made of dozens, sometimes hundreds, of tiny lenses composed of calcite. Unlike the soft tissues of many Cambrian animals, these hard lenses fossilized with remarkable clarity, preserving the intricate structure of vision from 500 million years ago. When viewed under magnification, the details of these ancient eyes still glint in the stone, a direct record of sight that reached across time. For trilobites, these eyes meant awareness. They could scan their surroundings for predators gliding above or for smaller prey and scraps along the seafloor. With wide fields of vision, some nearly panoramic, trilobites became alert participants in the unfolding drama of predator and prey. Their ability to detect sudden motion gave them precious moments to roll into a ball or scuttle for safety. Vision allowed them to react, and in those reactions lay survival. Predators too benefited from sight. Anomalocaris, with its swift swimming flaps and grasping claws, is thought to have had large, sophisticated eyes, each bearing thousands of lenses. With such vision, it could track the movements of prey in dim water, focusing on fleeing trilobites or soft-bodied animals trying to vanish into the mud. To see was to hunt more effectively, and in turn, to place greater pressure on prey to evolve defenses. The balance of power tilted back and forth, each improvement in eyesight demanding sharper strategies of evasion and protection. The rise of eyes reshaped the very landscape of the Cambrian seas. Burrows became deeper, camouflage more elaborate, armor more common. The act of seeing forced the world into constant vigilance. It was no longer enough to simply exist. Creatures had to anticipate one another, to outpace or outwit, to notice the shimmer of danger before it struck. Sight turned the oceans into an arena of awareness, where invisibility or surprise meant life, and hesitation meant death. The story of vision in the Cambrian is more than a tale of adaptation. It is the beginning of a sensory revolution that has continued ever since. Eyes connected animals to their surroundings in ways no earlier sense had managed. They allowed the perception of landscapes, of movement, of detail, and eventually, in distant ages, of color and depth. From the glinting compound eyes of trilobites to the keen gaze of modern predators, the roots of sight reach back to these ancient waters. And as eyes sharpened, the seafloor itself became a record of movement and interaction, marked by trails and impressions left by creatures reacting to what they saw, setting the stage for the busy battlefield of life beneath the waves. Beneath the shifting waters of the Cambrian oceans, the seafloor was alive with activity. What had once been a flat, quiet landscape coated in microbial mats became a place of constant disturbance. Burrowers dug through the soft sediment, overturning the carpets of bacteria that had dominated earlier ages. With each movement, the seafloor changed shape, and the calm blankets of microbial life were replaced by shifting mosaics of trails, tunnels, and mounds. The microbial mats themselves were ancient structures. For billions of years, they had formed thin, layered sheets of cyanobacteria that stretched across vast areas of seafloor. They trapped and bound sediment, creating stable surfaces that other organisms could cling to or graze upon. In the Precambrian world, these mats were among the few sources of structure in otherwise simple environments, but in the Cambrian they began to vanish. The new burrowers shredded them, tunneling beneath and through them, leaving behind churned sediments instead of still surfaces. In their place, a new kind of ecosystem emerged, one built on motion and disturbance rather than stability. These burrows and trackways left marks that can still be read in the rocks today. Fossils do not preserve only bodies, they also capture the traces of behavior. The Cambrian layers are filled with strange patterns pressed into ancient mud, thin, sinuous trails that mark the wanderings of soft-bodied animals, tiny pits where creatures dug briefly in search of food, and deep horizontal tunnels that show where organisms sought safety from predators. Some trackways form loops and spirals, suggesting aimless foraging, while others cut straight lines across the seafloor, the paths of determined movement. Each one is a shadow of an animal long gone, a fossilized moment of its life. The increase in these traces is one of the clearest signs of how complex the Cambrian world had become. In earlier ages, the seafloor bore few such marks. Microbial mats were largely undisturbed, and organisms that moved across them left little behind. Now, the sediment became a canvas of interaction, a living battlefield where the struggle between predator and prey, grazer and burrower, was written into the very ground. This new activity reflected the complexity of food webs that had begun to take shape. Energy no longer passed through the simple loops of microbes and grazers that had once defined the oceans. Now there were multiple layers of interaction. Small filter feeders pulled nutrients from the water. Grazers scraped at surfaces, consuming algae or bacteria. Burrowers sifted through mud for organic material. Larger hunters preyed on the smaller ones, while scavengers followed behind, feeding on remains. At the top, predators like Anomalocaris swept through, their movements disturbing everything in their path. Each level of this web depended on the others, creating a network of relationships that pulsed with constant tension. The battlefield of the seafloor was not only about combat or chase, it was about adaptation. Every tunnel, every track, every overturned mat represented an animal finding its way to survive in a world of growing pressures. Some found safety by digging deep, vanishing into the darkness below. Others relied on speed, dashing across the surface before danger could catch them. Still others trusted to armor or spines, leaving heavy impressions as they moved. The traces of these strategies linger in the rock, silent yet eloquent evidence of the lives that once stirred the mud. For paleontologists, these trace fossils are as important as the bodies of the creatures themselves. They reveal not only what these animals looked like, but how they lived, how they moved, and how they interacted. Together, they tell a story of a seafloor no longer quiet but restless, alive with the endless give and take of survival. The Cambrian seas had become woven with complexity, and in certain places on Earth, conditions would preserve this richness in astonishing detail, capturing not only the outlines of bodies, but the fleeting forms of soft tissues that rarely survived elsewhere. High in the Canadian Rockies, where jagged peaks rise into thin air and snow lingers on the ridges even in summer, lies a place that holds a secret from 500 million years ago. At first glance, it seems an unlikely setting for one of the most important fossil sites on Earth. Yet, within the dark layers of stone at a place called the Burgess Shale lies a window back to the Cambrian seas, a record so vivid that it feels as if time itself pressed pause. The Burgess Shale was first discovered in the early 20th century by Charles Doolittle Walcott, an American paleontologist who stumbled upon fossils while exploring the mountains of British Columbia. What he uncovered there would reshape the understanding of life's early history. Until then, most fossils from the Cambrian were of hard parts, like shells and exoskeletons, creatures such as trilobites, whose mineralized armor preserved easily. The soft-bodied animals that made up much of the Cambrian world were thought to have vanished without trace, their delicate tissues too fragile to survive the ages. But in the Burgess Shale, something extraordinary had happened. Here, entire communities were preserved in exquisite detail, including soft-bodied animals that rarely left fossils anywhere else. Creatures with tentacles, fronds, flaps, and delicate filaments appear pressed into the shale as if caught in the very moment of their existence. Even the faint outlines of muscles and digestive tracts can be traced. These fossils are not just shadows of hard shells, but full portraits of animals whose bodies were mostly flesh, creatures that otherwise would have been lost to time. The reason for this remarkable preservation lies in the setting. 500 million years ago, the region that is now the Rocky Mountains was part of a warm, shallow sea. Near the edge of an underwater cliff, mudslides occasionally swept creatures from the seafloor into deeper waters, burying them quickly in fine sediment. Cut off from oxygen and scavengers, their bodies lay undisturbed long enough for impressions of even the softest tissues to be captured. Over millions of years, these layers hardened into shale, sealing within them a record of a vanished world. The diversity revealed by the Burgess Shale is breathtaking. Hallucigenia, with its spines and stilt-like legs, is known to us largely because of these deposits. Opabinia, with its 5 eyes and flexible trunk, emerged from these stones, reconstructed with features so strange that its first presentation to scientists was met with disbelief. Wiwaxia, bristling with scales and spines, also came from here, its defensive body plan etched into the rock. Alongside them are dozens of other species, many with no modern relatives at all, each one showing the experimental spirit of evolution during the Cambrian Explosion. The fossils of the Burgess Shale demonstrate just how many ways life tested itself in that brief burst of time. Some animals bore traits that hint at future lineages, the first steps toward arthropods, mollusks, or chordates. Others appear as isolated experiments, body plans that had no future but still filled their roles in the ecosystems of their day. The sheer number of unique forms preserved here suggests that the Cambrian seas were teeming with life, far stranger and more varied than once imagined. Looking into these stones is like gazing through a window into an alien ocean. Flattened though they may be, the fossils whisper of creatures creeping, swimming, filtering, and hunting. Their preservation lets us imagine the details that would otherwise be lost: the flick of a fin, the ripple of soft tissue, the gleam of eyes that once scanned the seafloor. The Burgess Shale shows that the Cambrian Explosion was not just a moment of innovation, but a flourishing of entire ecosystems, rich and intricate, layered with interactions. The discovery of this site expanded the understanding of early life dramatically. What had seemed like a sudden rise of armored forms now appeared as a true explosion of diversity, including soft-bodied animals as central players. The Burgess Shale revealed that the Cambrian seas were filled not only with trilobites and predators, but also with countless fragile forms whose bodies would have vanished without this rare stroke of geological fortune. As scientists studied these fossils, they began to search the world for other sites with similar preservation, and in time, more would be found, scattered across continents, each offering its own view of Cambrian ecosystems and together building a global picture of this extraordinary age. Far across the world from the Canadian Rockies, in the rolling hills of Yunnan province in southern China, lies another window into the Cambrian seas. This place is called Chengjiang, and within its quiet layers of stone lies an archive of life just as extraordinary as the Burgess Shale, but even older. While the Burgess fossils captured a flourishing community around 505 million years ago, Chengjiang reaches deeper into time, preserving creatures from nearly 518 million years ago. It is one of the earliest glimpses we have of the Cambrian Explosion in motion, as strange life forms first began to rise and diversify. The Chengjiang fossils are astonishing in their clarity. Tiny filaments of gills, the delicate outlines of soft tissues, even the traces of internal organs are preserved. When the layers are split apart, they reveal creatures that would otherwise have vanished completely. Here, we see some of the earliest known chordates, small fish-like animals with notochords, the flexible rods that represent the earliest backbones. From these simple beginnings would one day emerge all vertebrates, including fish, reptiles, birds, and mammals. In Chengjiang, the roots of our own lineage can be traced, lying quietly beside creatures so alien they seem from another world. What makes Chengjiang so remarkable is the sheer diversity of forms preserved there. Spiny worms, delicate filter feeders, predators with grasping appendages, and tiny swimming arthropods appear side by side. The fossils suggest a thriving ecosystem with layers of interaction, where grazers sifted through microbial mats and larger hunters prowled for prey. In these ancient rocks, the Cambrian seas of China come alive, showing not just individual species, but entire communities frozen in time. Far to the north, in the icy wilderness of Greenland, another treasure was found at a site called Sirius Passet. This location, discovered in the early 1980s, offers its own unique perspective. Sirius Passet dates to roughly the same age as Chengjiang, yet the animals it preserves are somewhat different. The fossils include creatures with shield-like heads, elongated worm-like forms, and arthropods with unusual body plans. The conditions in this Arctic region captured life in a way that complements what is seen elsewhere, expanding the picture of Cambrian diversity. Together, these fossil sites begin to reveal that the Cambrian explosion was not a localized event, but a truly global transformation. In Canada, China, and Greenland, the layers of stone whisper the same story. Life was experimenting wildly, filling oceans across the planet with new and complex forms. The differences between the sites highlight how ecosystems varied from place to place. In Chengjiang, the warm, shallow seas of southern China supported a rich mix of delicate filter feeders and early chordates. In the Burgess Shale, deeper waters at the base of an underwater cliff captured predators and scavengers swept down by mudslides. In Sirius Passet, harsher Arctic conditions preserved communities that adapted to a different kind of seafloor environment. The Cambrian seas were not uniform. Plate tectonics had scattered continents into new positions, and shallow continental shelves wrapped around the edges of landmasses. Each of these shelves became a stage for evolution, with local conditions shaping the creatures that lived there. Nutrient levels, currents, and sediment patterns all varied, giving rise to ecosystems that shared some common players, but also developed unique casts of life. The more fossil sites that are discovered, the clearer it becomes that the Cambrian explosion was not a single story told in one place, but a chorus of overlapping experiments happening across the world's ocean. When these fossil deposits are compared side by side, the global picture grows sharper. Chengjiang reveals the earliest roots of lineages that would endure through deep time. The Burgess Shale shows how those lineages branched and flourished into extraordinary variety. Sirius Passet adds its own cast of unusual organisms, many of which are still difficult to classify. Each site adds detail to the great puzzle of how life transformed in that brief evolutionary burst. Without all of them, the story would be incomplete. The preservation of such sites is also a reminder of how rare and fragile our windows into deep time are. Conditions must align perfectly for soft-bodied animals to fossilize, and it is only through chance that mudslides, fine sediments, and low oxygen combined in places like Chengjiang and Sirius Passet. These accidents of geology became time capsules, holding secrets for hundreds of millions of years until the right eyes came along to uncover them. As paleontologists continue to search, more Cambrian fossil sites are found in different corners of the world, each one adding new creatures and new perspectives. The growing map of discoveries reveals not just isolated snapshots, but a global panorama of a planet that was alive with invention, each ocean basin a laboratory of evolution. Among the many fossils that emerge from Cambrian rocks, there is one delicate creature that has become almost a symbol of its age. Paleontologists named it Morella, and in the Burgess Shale alone, more than 20,000 specimens have been found. Each one is small, no longer than a fingertip, yet together they tell a story of extraordinary abundance and variety. Morella belonged to the arthropods, the group that would become the most successful and numerous phylum on Earth. Even today, arthropods account for the majority of all known animal species, and their roots stretch back into these ancient seas. The body of Morella was segmented, its outline resembling a tiny armored boat with spines and sweeping appendages. Along its sides sprouted jointed legs, while long spiky projections extended backward like delicate streamers. It was not large, and it probably swam or drifted close to the seafloor, but its structure showed the key innovations that would allow arthropods to conquer nearly every habitat on Earth. Segmentation gave flexibility and adaptability, allowing body parts to specialize. Some legs could become paddles, others pincers, others delicate feelers. Over time, this modular system would give rise to crabs, spiders, insects, and countless other forms. The exoskeleton was another essential breakthrough. In Morella, the outer body was thin and fragile, yet it marked the beginning of a strategy that would define the arthropods. By encasing the body in a protective shell of hardened material, animals gained defense against predators and a framework for powerful muscles. The shell also created challenges, such as the need to molt in order to grow, but the advantages far outweighed the difficulties. With each new generation, exoskeletons became stronger, more elaborate, and more versatile. The Cambrian seas were filled with other arthropods too, showing just how explosive this group had become. Some were simple, scuttling forms that grazed across microbial mats. Others were swimmers with paddle-like limbs that carried them swiftly through the water. There were early predators with clawed appendages, designed for grabbing and tearing prey. There were filter feeders with feathery limbs that sieved particles from the water. The sheer diversity is staggering, with hundreds of different body plans captured in the stone. Each variation was a new experiment, a test of what worked and what failed in a world of constant change. One of the most extraordinary features found in these arthropods was the compound eye. While trilobites possessed some of the most advanced versions, even tiny forms like Morella displayed complex arrangements of lenses that provided a wide and detailed view of the world around them. In an ocean where predators lurked and prey had to stay alert, vision became a decisive advantage. The compound eye was so successful that it still exists largely unchanged in insects and crustaceans today, a direct inheritance from the Cambrian seas. What makes Morella so fascinating is not just its delicate beauty, but also what it represents in the broader story. It was part of an explosion that would eventually shape entire ecosystems on land and in the air. Every insect that buzzes today, every spider that spins a web, every crab that scuttles along a shoreline owes something to these early Cambrian ancestors. The modular body plan and armored exoskeleton became a winning combination, one that would outlast entire dynasties of other creatures. The fossil record shows that arthropods did not remain confined to one shape or size. Some evolved streamlined swimming forms, others grew spines and thick shells. Some specialized as scavengers, while others became agile hunters. The Cambrian period was their testing ground, a place where the possibilities of segmentation and exoskeletons were explored in countless directions. Each adaptation fed into the larger web of survival, influencing how predators hunted and how prey defended itself. As we look at Morella and its kin, we see more than ancient animals trapped in stone. We see the earliest outlines of a story that continues today, a story of resilience, adaptability, and innovation. The arthropods were not just participants in the Cambrian seas, they were pioneers, laying down patterns of design that evolution would return to again and again. From their fragile bodies, encased in delicate armor, would come the great swarm of life that now dominates our planet in both diversity and sheer numbers. The Cambrian seas were alive with possibilities, and within those waters, the arthropods carved out their place, setting the stage for a lineage that would endure through mass extinctions and global changes. Their success would ripple outward, shaping ecosystems across the globe, and their story began with small, delicate creatures like Morella, captured forever in the rocks of the Burgess Shale. Beneath the surface of the Cambrian seas, change was not only visible in the shapes of bodies, but hidden deep within the code of life itself. While predators and prey were testing new strategies in the open water, a quieter revolution was unfolding inside their cells. This revolution was guided by a set of master switches known as Hox genes, a genetic toolkit that would become one of the most powerful engines of evolution. Hox genes can be thought of as the architects of the body. They do not build tissues directly, but they control when and where other genes are turned on. In the simplest sense, they provide instructions. This part of the body will become a head. This part will grow limbs. This segment will sprout eyes. Without them, bodies would have no clear map, only a blur of repeating parts. With them, the body could become a series of coordinated regions, each one specialized for a different role. Before the Cambrian, life was simple. Soft-bodied organisms drifted through the seas, with little distinction between one part of the body and another. But once Hox genes began to multiply and diversify, they opened doors that had been closed for billions of years. Segments could take on different identities, creating heads, tails, claws, or wings. Limbs could develop in new places, eyes could sprout in clusters. Entire new body plans could be imagined, tested, and lived out within the span of a single evolutionary heartbeat. In creatures like arthropods, the impact of Hox genes was dramatic. Segmented bodies became canvases for endless variation, with some segments bearing walking legs, others sprouting antennae, and still others developing into protective shields. In early chordates, Hox genes guided the development of a notochord and arranged the nervous system along a central line. This same genetic toolkit is still at work today, shaping embryos as they grow into fish, birds, reptiles, and humans. The blueprint of our own bodies can be traced back to the silent instructions of these ancient genes. The flexibility of this toolkit explains why evolution suddenly seemed to have so many options during the Cambrian Explosion. For billions of years, life had been limited by simple genetic controls, producing organisms that were repetitive and restrained. With the rise of Hox genes, the same stretch of DNA could be reused in countless ways, orchestrating complex structures without reinventing the wheel. It was as if evolution had discovered not just a hammer and chisel, but an entire toolbox filled with instruments capable of carving intricate designs. The discovery of Hox genes in modern science has been one of the most astonishing insights into the history of life. Scientists found that the same clusters of genes that shape a fly's segmented body also guide the development of a mouse or a human. These genes are ancient, conserved across 500 million years, passed down like a universal language spoken by all complex animals. The arrangement of a spine, the position of limbs, even the layout of the face, all depend on instructions first written in the Cambrian seas. The Cambrian Explosion, then, was not only an ecological drama of predator and prey, it was also a genetic awakening. With Hox genes providing a flexible script, evolution could rewrite its characters with remarkable speed. Some experiments produced lasting designs, like the segmented bodies of arthropods or the notochords of early vertebrates. Others vanished, strange creatures that left no descendants, but each attempt was guided by the same hidden toolkit, reshuffling the parts of life into new arrangements. In the fossil record, the results of this revolution appear as sudden diversity, a riot of unfamiliar shapes. Yet behind every spine, claw, or eye was the silent work of genes turning on and off in patterns that had never existed before. The ocean became a living laboratory where these instructions were tested again and again, creating forms that would dominate the seas and later spill onto the land. The power of Hox genes lies not in their complexity, but in their simplicity. With a handful of master switches, life gained the ability to explore countless designs, to shape bodies with purpose and direction. The Cambrian seas were filled with predators chasing prey, but they were also filled with invisible codes, writing the future of all animals. And from those codes, the story of every creature, from trilobite to human, would eventually unfold. In the quiet depths of the Cambrian seas, a profound transformation was taking place. Until this moment in Earth's history, most creatures had bodies that were soft and vulnerable. They drifted or crawled without much protection, their forms preserved only rarely in the sediments of the ocean floor. Then, in a geological instant, something new appeared. Animals began to draw minerals from the seawater, weaving them into their very bodies. Out of calcium carbonate and phosphate came the first skeletons and shells, a change that would alter not just the creatures themselves, but the entire course of life on Earth. At first, these hard structures were small and simple, little more than tubes or cones encasing delicate organisms. Some of the earliest examples are found in fossils called small shelly fauna, tiny fragments that look like beads, scales, or spicules scattered in the rock. They may not look like much, but they were the first hints of an extraordinary new strategy. By hardening parts of the body, animals gained a measure of security in a world that was growing increasingly dangerous. Predators with grasping claws and spiked appendages were on the rise, and those without protection became easy meals. A thin layer of mineral could mean the difference between survival and destruction. As this innovation spread, skeletons and shells took on many shapes. Some animals grew external armor, turning their bodies into protective fortresses. Others formed internal supports, giving them strength and structure from within. The minerals themselves varied. Calcium carbonate, the substance that would later build coral reefs and clamshells, became a common choice. Calcium phosphate, the mineral found in our own bones and teeth, also began to appear. Each had its advantages, and different lineages explored different possibilities. The impact was enormous. With shells, animals could burrow into the sediment more effectively, anchoring themselves against currents. With skeletons, they could grow larger and move with more power, muscles pulling against rigid supports. New feeding strategies emerged, as strong jaws and teeth allowed creatures to crush or scrape food sources that had once been inaccessible. The seafloor, once covered in soft microbial mats, became a landscape of armored grazers, burrowers, and hunters. The rise of skeletons also changed the fossil record forever. Before this time, only rare conditions allowed soft-bodied creatures to be preserved, and much of early life slipped away without a trace. But shells and bones fossilized readily. They were durable, resisting decay and pressure, leaving behind a lasting imprint in the rocks. From this point on, the story of life became far more visible. The abundance of shells in Cambrian sediments is like a sudden chorus in the geological record, a signal that life had discovered a way to make itself permanent. The influence extended beyond biology and into geology itself. As billions of small shells accumulated on the ocean floor, they began to shape the very fabric of Earth. Over long spans of time, their remains compressed into thick layers of limestone and other sedimentary rocks. Entire mountain ranges now bear the traces of those ancient shells, lifted by tectonic forces to heights far above the seas where they were first laid down. The cliffs that line coasts, the peaks that pierce the sky, many are built from the remains of tiny Cambrian skeletons. This transformation was not without cost. The production of skeletons required energy, and molting brought moments of vulnerability as arthropods shed their exoskeletons to grow larger. But the survival edge was undeniable. In an ocean where predation was escalating, hard parts provided defense, mobility, and opportunity. They allowed bodies to be reshaped into new forms, some with spiny armor, others with powerful jaws, and still others with intricate shells coiled into spirals. From these beginnings, the use of biominerals spread through nearly every major group of animals. The legacy continues in the bones that hold up our own bodies, in the enamel of our teeth, and in the shells that still wash up on modern shores. The Cambrian seas were the birthplace of this innovation, and from then on, life would carry with it the memory of stone woven into flesh. The Cambrian seas were not only filled with strange and alien shapes, they were also bound together by a new and intricate web of life. For billions of years before this period, food chains had been simple. Microbes floated through the water, forming mats on the seafloor, and the organisms that lived off them were limited in number and design. But in the Cambrian, everything changed. As bodies grew more complex and strategies for survival multiplied, the flow of energy through the oceans transformed into something far richer and more dynamic. At the base of this new web were the algae. These microscopic plants and plant-like organisms use sunlight to build energy, drifting in the water as phytoplankton or spreading across surfaces in thin films. They were abundant, invisible to the naked eye, yet powerful enough to sustain entire ecosystems. Tiny grazers scraped them from microbial mats, while filter feeders sieved them from the water. This invisible foundation carried the weight of everything above it, just as grasses and leaves would one day carry the herds of the land. Hovering above the mats or gliding through the water were the filter feeders. Some, like sponges, passed currents of water through their porous bodies, extracting the smallest particles. Others had rows of feathery limbs, sweeping food into their mouths. These creatures were quiet collectors, turning clouds of drifting cells into nourishment, and in doing so, they tied the microscopic world to the larger, visible one. Their role was essential, for without them the energy created by algae would have remained out of reach for larger animals. Grazers added another layer. These were animals that moved across the seafloor, scraping at microbial mats or nibbling on growing films of algae. Trilobites filled this role in many places, using specialized mouthparts to grind and consume. Their trails are still visible in ancient rocks, winding patterns etched into sediment that tell of endless foraging. Grazers became the link between the stability of the seafloor and the hungry mouths of predators, passing along energy in the form of their own bodies. Then came the scavengers, the cleaners of the Cambrian seas. Whenever a creature died, its body became an opportunity. Worms, arthropods, and other opportunists picked apart carcasses, recycling nutrients back into the system. Nothing was wasted for long. Even in these early oceans, the circle of consumption was already turning, with every death feeding new life. Scavengers played their part quietly, yet without them the web would have broken under its own weight. Above them were the hunters. These were the animals that changed the game forever, creatures like Anomalocaris with its grasping appendages and circular mouth, or smaller predators with spines and sharp claws. They stalked the grazers and filter feeders, driving them into burrows or forcing them to evolve new defenses. Their attacks rippled outward, shaping the behavior of every animal around them. Predation introduced urgency into the seas, a constant tension between vigilance and hunger. The result of these layers was complexity unlike anything the world had seen before. Energy moved through the Cambrian oceans in many directions. Algae fed filter feeders and grazers. Grazers and filter feeders became food for scavengers and hunters. Hunters fed upon one another, sometimes falling victim to their own kind. Scavengers returned the remains to the system, where microbes completed the cycle. It was no longer a simple chain but a web, woven tightly with countless strands. This complexity carried profound consequences. With so many roles to fill, niches multiplied. Animals began to specialize in ways they never had before, adapting to tiny differences in habitat, food, or behavior. Some learned to burrow deeply, some to swim faster, some to develop spines or shells, and others to hunt in new ways. Each adjustment fed back into the web, creating new opportunities and new challenges. The Cambrian seas, once quiet and uniform, became arenas of interaction. Every creature was tied to every other, whether as hunter, prey, scavenger, or competitor. The food web was more than a way to distribute energy. It was the very engine of evolution, driving the innovations that made the Cambrian explosion so sudden and dramatic. What had once been a flat and simple system now pulsed with complexity, and from that complexity came resilience, diversity, and the boundless experimentation of life. For billions of years before the Cambrian, the seafloor was a quiet place. Microbial mats spread across the sediment like carpets, binding the grains together into firm, stable layers. These mats created a world of stillness where few disturbances broke the surface. Small organisms lived on top of them, scraping at their edges or drifting above, but almost nothing ventured below. The seafloor was flat, firm, and predictable. Then, during the Cambrian, animals began to dig. At first, the traces were shallow, faint lines etched just below the surface. Over time, they grew deeper and more complex, twisting passages that tunneled into the sediments and overturned the stability that had lasted for eons. Burrowing became one of the great innovations of the age, and with it came an ecological revolution that reshaped the foundation of marine life. The appearance of burrowers transformed the seafloor in ways both subtle and profound. Microbial mats that had once held the sediments together were ripped apart. Instead of a smooth, crust-like surface, the ocean floor became churned and disturbed. Grains of sand and mud were loosened, oxygen could filter deeper into the ground, and nutrients buried within the layers were released back into circulation. The very chemistry of the seafloor began to change, creating new opportunities for organisms that could exploit these disturbed environments. The burrowers themselves were a varied group. Some were small worms that wriggled just beneath the surface, leaving behind trails like tiny strings pressed into the sediment. Others carved spiral burrows that plunged deeper, twisting paths that sometimes rejoined the surface in multiple places. Certain arthropods created branching tunnels, networks that look almost architectural when preserved in the rock. These burrows were more than shelters. They were feeding grounds, places to sift through grains for organic matter, or safe zones to hide from predators. Each tunnel was a new way to survive in a seafloor that was becoming increasingly crowded and dangerous. The destruction of microbial mats may sound like a loss, but it was also the beginning of a new kind of ecosystem. When the mats were intact, they limited how far animals could penetrate, creating a rigid environment that allowed little innovation. Once the mats were broken apart, the sediments became softer, more oxygenated, and more dynamic. Animals could now exploit food buried below the surface, creating a new dimension of life. Instead of being confined to the water above or the surface itself, the ocean floor became a three-dimensional environment filled with hidden niches. The evidence of this revolution is found not only in the fossils of animals themselves, but in the trackways and burrows that they left behind. These trace fossils, as scientists call them, are among the clearest signals of the Cambrian explosion. In layers of rock, simple surface trails suddenly give way to deeper, more complex networks. The patterns show a progression of experimentation, from tentative scratches to elaborate systems that could only have been made by animals with advanced behaviors. These markings are a direct record of activity, frozen moments of animals moving, hiding, and feeding 500 million years ago. The Cambrian substrate revolution also reshaped the food web, with burrowers constantly disturbing the sediments. Nutrients once locked away in the mats were freed for others to use. This recycling fueled the growth of new communities, supporting more grazers, scavengers, and predators. The seafloor, once a stable carpet of microbial growth, became a turbulent and unpredictable landscape, alive with movement both above and below the surface. It was a fundamental ecological shift. The old world of calm mats and still sediments was replaced by one of constant turnover, a living battlefield where every grain of sand might be stirred by the movement of an animal. The burrowers did not just change their own way of life, they changed the entire stage on which life unfolded, opening the seafloor to possibilities that had never existed before and setting the pattern for marine ecosystems that continues to this day. The Cambrian seas shimmered with possibility. New creatures filled the water, each carrying bodies assembled in unfamiliar ways, their outlines strange and untested. Some would prove to be blueprints for the future, ancestors of the arthropods, mollusks, and chordates that still thrive today. Yet many others were fleeting experiments. Their forms dazzled for a moment in deep time, then faded, leaving no descendants behind. These are the evolutionary failures, the bodies that did not endure, yet whose presence was vital in shaping the history of life. One of the striking things about the Cambrian explosion is the sheer variety of body plans that appeared. Scientists use the term body plan to describe the basic layout of an animal's form, the arrangement of its symmetry, limbs, organs, and skeleton. In earlier ages, there had been only a handful of patterns. In the Cambrian, dozens erupted at once, as if evolution were sketching and redrawing possibilities in rapid succession. Some were refined into lineages that would last 500 million years. Others vanished almost as quickly as they appeared. Among the strangest were animals like Opabinia, with its 5 eyes and trunk-like appendage. Its uniqueness is so striking that scientists often place it in its own category, disconnected from any modern relative. Another was Hallucigenia, with its spiny back and stilt-like legs, reconstructed at first upside down because it was so alien, though it may be loosely related to velvet worms that still crawl on land today. The original Cambrian form has no direct continuation. These creatures embody the sense of a world experimenting with forms, testing whether spines, eyes, or limbs arranged in new ways could work in a changing ocean. Some animals bore rigid plates in odd configurations, their shells arranged not as protective armor but as scattered patches, leaving much of the body exposed. Others had segmented bodies with limbs that seemed mismatched, some built for swimming, others for crawling, as if evolution had not yet decided what role the animal should fill. Fossils show worm-like creatures with bristles that went nowhere, shield-shaped heads without clear purpose, and jaws too delicate to catch or crush food effectively. Each of these designs tells a story of trial and error, of possibilities that were explored but ultimately abandoned. The failures were not wasted. By testing forms that did not last, evolution explored the edges of possibility, setting boundaries on what could survive in the harsh reality of predator and prey. A body that could not move efficiently, or a shell that offered little protection, or eyes that could not focus sharply enough, all these would be eliminated. But in the process, successful innovations were refined. Segmentation, exoskeletons, claws, and complex eyes emerged stronger because of the competition that swept away weaker designs. Scientists studying the Burgess Shale and Chengjiang often marvel at the variety of fossils that have no modern equivalent. Some are so unusual that they defy easy classification, placed in temporary categories with names like Problematica. Their very strangeness is evidence of how open the Cambrian world was, how many pathways life was willing to explore when given the tools of Hox genes and mineralized skeletons. For every success that led to enduring lineages, there were many failures that simply disappeared. Even the word failure is misleading, because in the grand scheme of evolution, these creatures were part of the process. They lived, reproduced, and shaped their ecosystems while they lasted. They served as prey, as competitors, as participants in the arms race of the Cambrian seas. Their disappearance was not meaningless, but part of the larger experimentation that allowed life to adapt and diversify. Without them, the path to successful designs might never have been found. The rocks preserve their brief stories in fine detail. Tiny spines, delicate eyes, or faint traces of appendages mark the outlines of lives that flickered and were gone. When we look at them now, they remind us of the impermanence of innovation, that not every idea endures, but each one contributes to the unfolding story. The Cambrian seas were alive with experiments, and though many vanished, their presence ensured that the survivors were stronger, sharper, and more resilient. The Cambrian seas, though alive with strange and thriving creatures, were far from stable. Beneath the shimmer of innovation and diversity lay fragility. Life was experimenting with forms it had never tried before, but it was doing so in an environment that could shift suddenly, tipping the balance from abundance to collapse. The Earth of 500 million years ago was not yet a gentle stage. It was a planet that pulsed with instability, and its oceans were prone to sudden changes that could snuff out entire communities. One of the greatest challenges came from fluctuations in oxygen. For animals that had only recently begun to depend on higher levels of oxygen for survival, these swings were perilous. Oxygen in the oceans was not evenly distributed. In shallow waters, waves and sunlight helped mix the gases, creating zones where life could flourish. But in deeper or more stagnant regions, Oxygen could vanish. When currents shifted or temperatures changed, those boundaries moved, and with them, the chances of survival. A thriving community might collapse in a single event as oxygen levels dropped, leaving behind only layers of sediment and the ghostly remains of its inhabitants. The fossil record bears traces of these upheavals. In some layers, rich assemblages of fossils are abruptly interrupted by barren sediments, as though life had been swept away in an instant. These interruptions speak of localized die-offs, mini extinctions that punctuated the Cambrian story. They were not global catastrophes like the great mass extinctions that would come later, but they still reshaped ecosystems, erasing lineages from one region while opening space for others to expand. In this way, the Cambrian explosion was not a steady climb of progress, but a stop-and-go pattern, surges of innovation interrupted by sudden setbacks. The fragility of life at this time was not only due to oxygen, the chemistry of the oceans themselves was unstable. Elements like carbon, sulfur, and iron shifted in balance, sometimes poisoning environments or reducing the resources available for survival. These changes could be triggered by volcanic activity, tectonic movements, or even the very organisms that were multiplying so quickly. As burrowers churned the seafloor and grazers disturbed microbial mats, nutrients were recycled in new ways, altering the chemistry of the water. What brought opportunity for some could mean disaster for others less adapted to rapid change. Even climate played a role. Although the Cambrian was generally warm, subtle shifts in temperature could ripple through marine ecosystems. Warmer waters hold less oxygen, compounding the effects of oxygen fluctuations. Currents that carried nutrients could weaken or strengthen, redistributing life from one coast to another. The continents themselves were scattered across the globe in smaller landmasses, their positions changing under the influence of tectonic drift, shaping shallow seas that could appear or vanish over geological timescales. Despite the flourishing diversity, these factors kept life precarious. The Cambrian seas may appear from the fossil record as a riot of abundance, but beneath that abundance was fragility, a sense that no ecosystem was fully secure. Creatures with delicate designs, specialized feeding habits, or narrow tolerances often vanished quickly, leaving behind only faint impressions in stone. The survivors were those able to endure instability, creatures with flexibility built into their bodies and behaviors. The many extinctions of the Cambrian remind us that evolution is not a smooth or gentle process. It is shaped as much by loss as by survival. Each localized die-off cleared ecological space, making room for new experiments to take hold. When oxygen levels rebounded, or when sediments stabilized, new creatures moved in, often stranger or more elaborate than the ones that had been lost. This cycle of fragility and renewal created a constant tension in the seas, one that fueled the creative energy of evolution, even as it caused suffering for the creatures living through it. The Cambrian explosion is often described as a burst of diversity, but it was also a fragile balance that teetered on the edge of collapse. The oceans of that time remind us that abundance and vulnerability can exist side by side, that innovation does not guarantee permanence. Beneath the beauty of those alien seas was a world of uncertainty, where every rise in complexity carried with it the risk of sudden loss, and where life, no matter how dazzling, remained delicate in the face of Earth's shifting conditions. When we imagine the Earth of the Cambrian period, it is important to remember that the continents we know today did not yet exist. The land was broken into smaller pieces, scattered across the globe like fragments of an unfinished puzzle. Vast oceans stretched between them, and the outlines of familiar places such as Asia, Africa, or the Americas had not yet taken shape. Instead, the world was dominated by a handful of ancient landmasses, each cradling shallow seas along its edges. These continents, Laurentia, Gondwana, Baltica, and Siberia, set the stage for one of the most important experiments in life's history. Laurentia, the landmass that would one day form the heart of North America, lay close to the equator. Its position gave it warm seas bathed in sunlight, conditions that nurtured thriving communities of algae, grazers, and predators. Along its shallow shelves, delicate creatures found both shelter and abundance. The Burgess Shale, discovered much later in the Canadian Rockies, preserves just a fragment of what lived along these margins. The fossils whisper of thriving ecosystems, but Laurentia's role in the Cambrian seas was far larger than any one site can reveal. Gondwana was by far the largest continent, sprawling across the southern hemisphere. It included pieces that would later separate into South America, Africa, Antarctica, India, and Australia. Its size meant that it touched many climatic zones, from tropical shallows to cooler waters near the poles. Along Gondwana's edges, new communities blossomed in tidal flats and submerged plains. Some of the earliest traces of burrowers and shelly fauna come from these regions, evidence that Gondwana was a hub of experimentation during the Cambrian. Its enormous coastlines provided more shallow shelf environments than almost anywhere else on Earth, and shallow shelves were where life found its greatest opportunities. Baltica, a smaller continent that would eventually join with Laurentia to help form Europe, drifted in the mid-latitudes. Its seas were also warm, and their sediments record trilobites and other arthropods in great numbers. These creatures thrived in shifting ecosystems shaped by changing currents, their fossilized remains scattered across layers of stone that tell of flourishing populations. Baltica's placement gave it rich marine habitats, even though it was dwarfed by the bulk of Gondwana. To the north sat Siberia, another smaller landmass that floated alone in the Cambrian seas. Though modest in size, Siberia also hosted its own ecosystems where trilobites and other early animals flourished. The isolation of this continent may have encouraged unique lineages to emerge, a reminder that geography often shapes the path of evolution as strongly as biology does. What tied these continents together was not their land but their seas. Around each landmass stretched wide continental shelves, shallow waters flooded by sunlight. These shelves were the nurseries of the Cambrian Explosion, places where life could multiply in vast numbers. Unlike the dark depths of the open ocean, the shallows were filled with nutrients carried from the land and stirred by currents. Here, algae grew in abundance, feeding filter feeders, which in turn fed grazers and predators. The shelves were cradles of energy, and the life that thrived on them became the heart of Cambrian ecosystems. Plate tectonics was the hidden engine behind all of this. Continents drifted slowly across the surface of the planet, pulled and pushed by the motion of Earth's mantle. As they moved, coastlines shifted, seas rose and fell, and habitats were created or destroyed. In some places, continents collided, lifting up mountains and cutting off shallow seas. In others, they pulled apart, opening rifts that filled with water and invited new communities to form. These shifts were slow by human standards, but across millions of years, they created a living, changing landscape that animals had to adapt to. The fragmented geography of the Cambrian world meant that evolution unfolded in many theaters at once. Along the shelves of Laurentia, trilobites and anomalocaridids hunted and grazed. In Gondwana's vast shallows, shelled creatures and burrowers left their marks in the sediments. In Baltica and Siberia, unique communities adapted to their own environments. Each continent carried its own cast of characters, yet together they told a single story of global transformation. The broken layout of the Earth gave the Cambrian seas a patchwork quality, with ecosystems shaped by local currents, climates, and coastlines. Life did not evolve in one uniform ocean, but in a mosaic of habitats scattered across the world. This patchwork fostered diversity, as creatures in one region adapted in ways that might not appear elsewhere. When continents later collided and merged, these lineages would meet, compete, and mingle, adding yet more complexity to the history of life. The Cambrian Explosion was not just a biological event, it was a geological one as well. The drifting continents, the shallow seas, and the restless motion of tectonic plates created the stage on which evolution's first grand drama played out. Without this fragmented world, the diversity that marked the Cambrian may never have reached such heights. The Cambrian seas were alive not only with new shapes and bodies, but also with motion. For billions of years before this period, movement had been simple and limited. Microbes drifted with currents, jelly-like forms pulsed weakly through the water, and mats of life clung to the seafloor. Then, during the Cambrian, animals discovered new ways of moving. They swam, crawled, and burrowed with purpose, turning still waters into landscapes filled with action. Every ripple, every track pressed into the sediment was part of a quiet revolution in how life interacted with its world. Swimming was one of the most transformative abilities. Creatures like Anomalocaris, with its broad flaps running along its sides, sliced through the water in pursuit of prey. Trilobites, though often imagined crawling along the bottom, could also paddle using rows of jointed legs. Some smaller arthropods used feathery appendages to push themselves upward, moving in schools or drifting in search of food. Swimming allowed animals to escape the seafloor and claim new spaces in the open water, turning the water column itself into a vast new habitat. The Cambrian oceans, once quiet layers of microbial haze, now churned with predators sweeping through the currents and prey darting away in quick bursts. Crawling offered another strategy. Trilobites in particular became masters of this form of motion, their segmented legs moving in waves beneath their armored bodies. Their trails are still visible in ancient rocks, parallel grooves and ridges that stretch across slabs of stone like frozen paths through a vanished world. Other creatures crawled more slowly, leaving delicate patterns as they grazed across microbial mats. Some pressed shallow furrows, while others left trackways that branched and looped, evidence of searching movements as they hunted or fed. These imprints, known as trace fossils, provide one of the most direct records of how Cambrian life interacted with the seafloor. They are not the bodies of animals, but the stories of their journeys, preserved in stone for more than 500 million years. Burrowing added yet another layer of innovation. Small worms wriggled below the surface, tunneling through sediments in search of food or refuge. Arthropods carved spirals and U-shaped tunnels, some branching in complex ways that suggest repeated use. These movements changed not only the animals' own lives, but also the world around them. By disturbing the sediment, burrowers released nutrients, oxygenated the seafloor, and created new microhabitats for other organisms. Their movements reshaped the environment itself, a form of engineering that altered the foundation of ecosystems. The once flat seafloor became riddled with passageways, each tunnel a hidden corridor of life. Fossilized trackways capture these movements in extraordinary detail. In slabs of rock, one can see the steady rhythm of trilobite legs, the meandering patterns of grazing creatures, or the sudden turn of an animal reacting to something unseen. Some tracks end abruptly, perhaps the moment a predator struck. Others show hesitation, as though the animal paused to test its surroundings. These silent marks are like signatures written in sediment, whispering of lives lived long before memory. Scientists often conduct movement experiments, comparing the fossils with modern arthropods or worms to understand how ancient animals used their limbs and bodies. Through this, the movements of the Cambrian seas come alive again, not just as static fossils, but as behaviors, choices, and actions. The new biomechanics of survival were as important as claws or eyes. With movement came freedom, but also risk. A creature that could swim fast gained access to prey, but needed speed to avoid becoming prey itself. Those that crawled slowly needed armor or camouflage to survive. Burrowers found safety underground, but at the cost of energy and constant labor. Every type of motion brought advantages and trade-offs, and in the Cambrian seas, those choices shaped who thrived and who disappeared. The Cambrian Explosion was not only about new forms of life, it was about new ways of living. Movement turned still seas into dynamic arenas where predator and prey danced in endless pursuit, where grazers left trails across microbial carpets, and where burrowers tunneled in secret beneath the surface. Each ripple of a fin, each stroke of a leg, each twist of a body in the sediment became part of an expanding story of survival and adaptation. The oceans were no longer quiet. They pulsed with life in motion, and that motion would carry forward into every age that followed. When we look at the Cambrian explosion in the fossil record, it appears as though life burst forth in a sudden and dazzling display, as if the oceans had gone from quiet to crowded almost overnight. But fossils are not the only way to measure time. Inside the cells of living creatures today lies another kind of clock, a silent record written in the language of DNA. Scientists call it the molecular clock, and it has opened a new dimension in our understanding of when life's great lineages began. The molecular clock works by measuring the slow and steady accumulation of mutations in genetic material. Over countless generations, DNA changes at a roughly predictable pace. By comparing the genetic differences between living animals, scientists can estimate how long ago their ancestors diverged from a common root. It is as if each group carries a ticking clock within its genes, marking the passage of deep time. When these genetic timelines are traced backward, a surprising picture emerges. The fossil record shows a dramatic bloom of animal life, beginning around 541 million years ago. Yet the molecular clocks often point to much earlier origins. They suggest that the ancestors of many major animal groups already existed tens of millions of years before their bodies first appear in stone. According to this genetic evidence, the roots of the explosion may stretch back into the late Precambrian, perhaps as far as 600 million years ago or more. This creates a tension between what is seen in the rocks and what is hidden in the genes. Fossils give us the hard evidence of shells, eyes, and segmented bodies, preserved in exquisite detail, but the DNA of living animals whispers of lineages that were already present long before those features appeared. Where are the missing forms that should fill this gap? Were they soft-bodied creatures that left no trace? Did they live in places where fossilization was rare, their delicate tissues dissolved before they could be captured in stone? Or does the molecular clock sometimes run too fast, exaggerating the depth of time? These questions remain at the heart of the Cambrian mystery. Some evidence hints at earlier complexity. In the Ediacaran period, just before the Cambrian, fossils of strange soft-bodied organisms appear. Many of them are so unlike modern animals that their relationships remain uncertain. Some may have been evolutionary dead ends, but others might represent the ghostly beginnings of lineages that would later bloom during the Cambrian explosion. Molecular clocks suggest that these shadowy organisms may be part of the story, early experiments that prepared the way for the explosion to come. The implications are profound. If animal lineages did indeed stretch back into the late Precambrian, then the Cambrian explosion was not a sudden creation of complexity from nothing. Instead, it may have been the visible flowering of branches that had been growing quietly in the dark for tens of millions of years. The explosion in the fossil record may reflect not the first appearance of animals, but the first time they gained features sturdy enough to leave lasting traces: skeletons, shells, and elaborate body parts that resisted decay. This blending of genetic evidence with fossils gives us a richer, though more complicated view of history. The rocks tell us what creatures looked like, how they moved, and what roles they played in their ecosystems. The DNA tells us when their lineages likely began, offering a hidden timeline that stretches back further than stone can show. Together, they remind us that no single record holds the entire truth. The Cambrian explosion was both a burst and a continuation, both sudden and long prepared. The molecular clocks continue to tick in every living cell, carrying forward the record of ancient divergence. When scientists compare genes from a jellyfish and a human, from a worm and an insect, they are hearing echoes of events that unfolded more than 500 million years ago. Each comparison is a reminder that the story of the Cambrian is not only written in stone, but also carried within the living fabric of our own bodies. The Cambrian world was bathed in warmth. Oceans stretched wide and welcoming, their waters free of the icy caps that now cover Earth's poles. The absence of frozen barriers meant that heat spread more evenly across the globe, smoothing away the extremes of temperature that can fracture ecosystems. The result was an age of remarkable climatic stability, a calm backdrop against which life could surge forward into new and untested forms. For billions of years before, the Earth had swung between harsh conditions. Snowball episodes had sealed the oceans under layers of ice, while hothouse periods had raised temperatures to extremes. These swings created barriers for the evolution of complex life, repeatedly resetting the stage before organisms could fully establish themselves. But by the dawn of the Cambrian, the climate had settled into balance. Global temperatures remained warm but not punishing. Seas were well mixed with sunlight and nutrients, and the absence of polar ice ensured that sea levels stayed high, flooding continental shelves with shallow, life-rich waters. It was in these broad, sunlit seas that the Cambrian explosion unfolded. Warmth spread across the equatorial waters, but even higher latitudes enjoyed relatively gentle climates. The circulation of ocean currents moved nutrients from place to place, supporting algae and other primary producers at a scale never before achieved. These microscopic engines of photosynthesis fed the filter feeders and grazers, which in turn supported predators. With the climate so steady, energy could flow without major interruption, creating webs of life that grew more intricate with every generation. The lack of ice caps meant more than warmth alone. Without glaciers locking away water, sea levels remained high, and shallow seas extended over large areas of the continents. These continental shelves, stretching for hundreds of kilometers in some places, were ideal habitats. Sunlight reached the bottom, fueling photosynthesis, while nutrients carried from the land or stirred by currents provided an endless banquet for early marine life. The sheer area of these shallow zones offered space for countless niches to develop, each one filled by a new experiment in body design. Stability also mattered. In later ages, sudden cooling events or rapid warming could devastate ecosystems, but in the Cambrian, fluctuations were muted. Generations of animals could rise, adapt, and diversify without being wiped away by sudden climatic shocks. This gave evolution the time and space to explore. Predator and prey pushed each other into new forms, while burrowers and grazers reshaped the seafloor. Complex ecosystems could build on themselves, layer by layer, because the environment provided a relatively steady stage. Evidence of this warm stability is found not only in the fossils, but in the rocks themselves. The chemistry of Cambrian sediments reflects oceans that were warm and oxygenated near the surface. Layers of limestone, built from the shells of tiny creatures, show how widespread and abundant life had become. These rocks form thick blankets across ancient continental margins, physical proof of seas that teemed with life in conditions that endured for millions of years. The warmth of the Cambrian seas also shaped the distribution of organisms. Without polar extremes, ecosystems could spread more widely. Creatures that might have been confined to narrow tropical bands in other times could range further, populating seas across continents separated by vast distances. This global spread is reflected in fossil sites around the world, from Laurentia to Gondwana, Baltica to Siberia, each revealing variations of the same great unfolding experiment in life. Yet the climate was not static in every detail. Local currents shifted, sea levels rose and fell gradually, and oxygen sometimes dropped in deeper waters. These changes brought challenges, and some communities disappeared when conditions turned against them. But compared to the upheavals of earlier Earth, the Cambrian was unusually gentle. Its relative calm gave fragile new body plans the chance to gain footholds, to be tested and refined in the long game of survival. The Cambrian climate was not merely a backdrop, it was an active partner in the drama of the explosion. By offering warmth without extremes, seas without ice, and shelves flooded with sunlight, it created the perfect incubator for diversity. The stability of this time fostered abundance, and in that abundance, evolution could take risks it had never taken before. Life could explore with freedom, and from that freedom came the astonishing variety that filled the Cambrian seas. As the Cambrian seas warmed and filled with life, something extraordinary unfolded beneath the waves. For the first time in Earth's history, the interactions among organisms reached a new level of intricacy. What had once been simple chains of energy, where microbes were consumed by small grazers and little more, began to blossom into layered networks of dependence, competition, and survival. It was here, in this brief but powerful window of time, that the first true ecosystems took shape. At the base of it all were the producers, microscopic algae drifting through the sunlit waters. These tiny organisms, harnessing sunlight and turning it into energy, formed the green foundation upon which everything else depended. Their abundance was supported by the nutrient-rich seas and by the gentle stirring of currents across wide continental shelves. They were consumed by filter feeders, creatures that strained the water for food, and by grazers that scraped microbial mats from the seafloor. In this way, energy captured from sunlight began to cascade upward through newly formed trophic levels. On the seafloor itself, animals left their marks in ways never seen before. Burrowers carved tunnels through the sediment, creating not just shelter for themselves, but entirely new microhabitats for smaller organisms. Grazers left trails across the mats they consumed, and scavengers followed the remains of other creatures, recycling nutrients back into the system. These subtle interactions may seem small, yet together they transformed the ocean floor into a patchwork of niches, each one filled with new possibilities. Above these base levels of life rose a second layer, filled with animals adapted to feed on the grazers and filterers. Many trilobites filled this role, moving across the seafloor in search of algae or soft-bodied prey. Other arthropods joined them, scraping, sifting, and experimenting with new ways of feeding. This middle tier was where diversity exploded, because every change in the availability of food created opportunities for fresh adaptations. A creature that could burrow deeper or swim faster found a way to survive, and in doing so, opened the door for predators to evolve in response. Predators were the final tier, the rulers of the Cambrian seas. Anomalocaris, with its ring of serrated mouthplates and grasping appendages, hunted the trilobites and other arthropods. Smaller predators, equipped with sharp spines, claws, or specialized mouths, filled in every available gap, ensuring that no resource went unused. With each new predator came pressure on prey species to adapt, and with each prey defense came fresh challenges for the hunters. This spiraling relationship fueled the rise of complexity, making ecosystems denser, richer, and more connected than ever before. The interactions among these layers were not simply predator and prey. Detritivores, feeding on decaying matter, tied the system together by returning nutrients to the base of the chain. Parasites may have already existed, exploiting hosts in ways that leave little fossil evidence, but that surely added to the web of connections. Even microbes still played a role, cycling chemicals and oxygen in the water, their ancient dominance woven into the new fabric of complexity. The multiplication of niches was one of the most profound outcomes of this age. In earlier times, an environment might hold only a handful of roles, each filled by simple organisms. In the Cambrian, niches expanded rapidly, splitting into countless specialized opportunities. One trilobite might specialize in burrowing in fine mud, while another evolved to scuttle across rocky surfaces. A predator might stalk in the open water, while another ambushed from the shadows of the seafloor. This proliferation created stability through diversity, as no single collapse could erase all forms of life. Evidence of these ecosystems is captured in the fossils themselves. Trackways etched into ancient sediments reveal the movement of hunters and the escape routes of prey. Burrows preserved in stone show where creatures once tunneled. Fossilized gut contents tell us what was eaten, while damage on trilobite shells reveals the bites of predators. Each piece of evidence is like a thread, and when scientists weave them together, a vast and intricate tapestry of life emerges, showing that the Cambrian seas were no longer quiet backdrops, but bustling communities of interaction. The rise of ecosystem complexity marked a turning point in the story of life. For the first time, survival depended not only on the environment, but on the endless interplay of species with one another. Competition, cooperation, predation, and defense became the driving forces of change. In this living battlefield of connections, evolution gained momentum, pushing organisms into ever stranger and more inventive forms. From this point onward, Earth would never again return to the simplicity of its early days. The Cambrian had unlocked the full power of interconnected life, and that power would carry forward into every age that followed. When we look back at the Cambrian seas, filled with creatures that seem as though they belong to another planet, it is tempting to think of this time as an exception, a brief flash of brilliance in an otherwise steady march of life. Yet the Cambrian explosion holds deeper lessons, patterns that repeat themselves across the history of Earth. One of the most striking is the way that innovation often comes not in a gentle climb, but in sudden bursts. For billions of years before the Cambrian, life had remained simple, mostly microbial, repeating the same basic patterns. Then, in what appears to be a geological blink, complexity unfolded with staggering speed. this is not the only time such a leap has happened. Much later, during the Carboniferous period, plants colonized land in new ways, building towering forests and releasing vast amounts of oxygen into the atmosphere. In the Triassic and Jurassic, the dinosaurs themselves took hold and spread into nearly every niche on Earth, giving rise to giants that roamed the land, flew through the skies, and swam in the seas. Again and again, history shows that change does not always proceed in steady steps. It gathers energy quietly, like pressure building deep beneath the surface, and then releases in waves of transformation. The Cambrian reminds us that life is not always gradual. It is often punctuated by bursts of creativity that alter the course of everything. One reason for this lies in thresholds, invisible boundaries that hold back change until the conditions are just right. In the Cambrian, rising oxygen levels, shifting oceans, and new genetic toolkits align to tip the balance. These thresholds can be thought of as gates in time, waiting for the right combination of keys. Before the gate is reached, evolution may circle and stall, unable to progress further. Once it opens, possibilities rush in, filling the world with new forms. Thresholds are not simply physical, like the amount of oxygen dissolved in the sea, but also ecological, as when predators first appeared and prey were forced to adapt, or genetic, as when the Hox genes allowed organisms to try out entirely new body plans. Each threshold is a point of release, a moment when potential energy is converted into living diversity. The Cambrian also teaches us that evolution is not a straight path toward improvement, but a process of trial and error. Many of the creatures that swam or crawled in those seas left no descendants. Their bodies were experiments, attempts at life's great puzzle that did not continue beyond that age. Hallucigenia with its spiny ridges, Opabinia with its 5 eyes and trunk-like appendage, and countless others were pathways explored and then abandoned. From our perspective, they seem strange, but to evolution, they were part of the same process of testing boundaries. Failure was not wasted effort, it was the fuel that made success possible. Without the discarded designs, there could be no refinement, no eventual rise of vertebrates, arthropods, and mollusks that still dominate today. It is easy to see failure as an end, but in the Cambrian, it was a constant background rhythm. For every creature that thrived, many more did not. Yet this constant experimentation increased the odds that some innovations would endure. The ability to burrow, the development of hard shells, or the evolution of vision were not inevitable outcomes. They were the results of countless trials, most of which vanished into the fossil record. What remained became the building blocks of all future ecosystems. In this way, the Cambrian shows us that impermanence and loss are as essential to life's story as persistence and survival. Even in its chaos, the Cambrian explosion reveals an underlying order, bursts of innovation, the crossing of thresholds, and the endless dance of trial and error continue to shape life on Earth to this day. Every forest, every coral reef, every grassland carries echoes of this first great experiment in complexity. What began in those alien seas established patterns that would repeat again and again through the vast span of deep time. As the Cambrian period drew to a close, the seas that had once seemed limitless in their creativity began to quiet. The explosion of body plans, the strange experiments of life that filled those alien oceans, started to fade. Many of the creatures that had once defined the Cambrian disappeared, leaving only their impressions in stone as evidence that they had ever existed. The diversity that had seemed so unstoppable was, in truth, fragile, and the end of this era would bring waves of extinction that reset the stage for what came next. The Cambrian was not ended by a single catastrophic event, like the asteroid that would one day wipe out the dinosaurs. Instead, its decline unfolded in pulses, a series of stresses that chipped away at the fragile new ecosystems. Fluctuations in sea levels created cycles of shallow seas, expanding and then retreating, stranding communities that depended on stable waters. Oxygen levels, which had once risen high enough to spark innovation, fell back in certain regions, leaving once thriving creatures struggling to survive in suffocating seas. Shifts in climate altered currents and disrupted the flow of nutrients, starving some ecosystems while flooding others with sediment. Creatures that had seemed perfectly adapted to the Cambrian seas suddenly faced challenges they could not overcome. Many of the experimental body plans already existing on the edge of viability simply disappeared. Hallucigenia, with its rows of spines and fragile legs, did not last into the next age. Opabinia, with its 5 eyes and peculiar feeding trunk, also vanished. Even the once dominant Anomalocaris, the terror of Trilobites, left no descendants to carry its line forward. These were designs that fit perfectly in the Cambrian moment, but when conditions shifted, they had no way to adapt. Yet extinction did not erase everything. Some groups proved resilient, carrying their innovations forward into the ages to come. Trilobites, with their hardened exoskeletons and adaptable forms, endured beyond the Cambrian, diversifying into hundreds of shapes that filled oceans for another 200 million years. Early brachiopods, filter feeders that anchored themselves to the seafloor, survived the changes and continued to thrive, becoming key players in Paleozoic ecosystems. Primitive mollusks also endured, carrying with them the genetic blueprints that would eventually lead to clams, snails, and cephalopods. Even the earliest ancestors of vertebrates, small and unassuming, managed to persist, holding within them the first steps of a journey that would one day give rise to fish, amphibians, reptiles, and eventually mammals. As the Cambrian gave way to the Ordovician period, life did not diminish, but transformed. The Ordovician seas would bring their own burst of diversity, filled with coral-like reefs, armored jawless fish, and vast populations of trilobites and brachiopods. Where the Cambrian had been about experimentation, the Ordovician was about expansion, a broadening of ecosystems that stabilized into more complex patterns. The fragile first attempts gave way to lineages that would endure longer and shape the future of the planet in ways the Cambrian pioneers never could. The end of the Cambrian was both a fading and a beginning. The bizarre creatures that defined it slipped into memory, but their influence lingered in the survivors who inherited the seas. The arms race of predator and prey, the tools of vision, armor, and skeletons, and the complex webs of interaction all carried forward. The Ordovician did not erase the Cambrian, it built upon it, like the next movement of a symphony rising from the echoes of the last. And so, even in extinction, the Cambrian remained the foundation, its vanished forms reminders that innovation is never without risk, and survival belongs to those who can weather change. As the seas shifted and new worlds began to rise, life prepared once again to astonish, carrying the legacy of the Cambrian into the unfolding chapters of Earth's deep history. Even though the Cambrian seas closed hundreds of millions of years ago, their presence has never truly vanished. The creatures that swam, crawled, or burrowed through those alien waters may be long extinct, but the blueprint they left behind is still with us. Every living being today, from the insects buzzing in the air to the fish gliding in the ocean, and even to us, carries within its body the deep echo of that ancient explosion. Arthropods, for instance, first appeared in those Cambrian waters. Their hard exoskeletons, segmented bodies, and jointed legs were innovations that allowed them to conquer nearly every environment. Trilobites, the earliest great representatives of this group, are gone, but their design has lived on in crabs, lobsters, spiders, and insects. The world we walk through now is largely theirs, as they make up the most diverse and numerous group of animals alive. When a dragonfly hovers above a pond, or when a beetle scurries across the soil, it is repeating a design first tested in those ancient seas. The mollusks, too, trace their ancestry back to Cambrian roots. In that period, soft-bodied creatures began experimenting with shells, discovering the strength that mineral armor could provide. Today's clams, snails, squids, and octopuses still carry that early invention, their bodies molded by the same choices that first gave rise to Wiwaxia and its bristled cousins. The iridescent curve of a seashell on the beach, the coiled whorls of a snail, or the graceful sweep of an octopus's tentacles are not just curiosities of nature, but living reminders of that first great wave of innovation. And then there are the vertebrates. In the Cambrian seas, they were nothing more than small, jawless forms, unremarkable beside the towering predators of their time. Yet they carried within them something extraordinary, a notochord that stiffened their bodies, paired with a nervous system that would one day grow into brains capable of memory, thought, and awareness. From those humble beginnings came fish, reptiles, mammals, and eventually humans. When we look at the fossil record of creatures like Pikaia, a worm-like ancestor that wriggled quietly on the Cambrian seafloor, we are looking at a shadow of ourselves. Even our eyes bear testimony to that era. The Cambrian was the time when sight first flourished, when trilobites developed compound eyes and predators learned to hunt by vision. That innovation was so powerful that it became permanent. Every time we blink, every time we take in the color of a sunset or the shimmer of water, we are making use of an evolutionary gift that was born in that ancient arms race. Our biology is filled with traces of Cambrian experiments. The segmentation of our spinal columns reflects the modular body plans that evolution first played with 500 million years ago. The way our genes shape development, guided by the ancient toolkit of Hox's genes, follows rules set down in those early days. Even the symmetry of our bodies, with left and right mirrored across a central line, is a legacy of Cambrian choices. These echoes extend far beyond humans. The buzzing of a bee, the coiling of a snail shell, the darting of a fish, and the intricate weave of a spider's web are all modern expressions of Cambrian inventions. The arms race of predator and prey, the building of armor, the creation of speed and stealth, and the invention of skeletons and shells continue to shape life on Earth today. The Cambrian was not only a beginning, it was the foundation of nearly everything that followed. To look around at the living world is to glimpse a tapestry woven from threads that stretch back into those ancient seas. The shapes of animals, the ways they move, the senses they use, even the structures of our own bodies, all carry whispers of a time when evolution discovered complexity for the first time. And though the Cambrian itself is long gone, it has never truly ended because it lives within us, beating quietly in the rhythm of every heart and unfolding in the growth of every living cell. Even after decades of study, the Cambrian explosion remains one of the most debated puzzles in the history of life. The rocks tell us that in a span of time that feels like the blink of an eye compared to Earth's long history, simple seas filled with microbes and soft-bodied forms gave way to a riot of complex animals. Every major group of life seems to trace its ancestry back to this window, yet when scientists ask why it happened, no single answer fits neatly. Some believe oxygen was the key. Before the Cambrian, oxygen in the oceans was scarce, and life was often limited to shallow or patchy environments. Then levels began to rise, giving animals the fuel they needed to build skeletons, develop muscles, and support energy-hungry organs like eyes and nervous systems. The timing fits, but oxygen alone cannot explain why such extraordinary diversity appeared in so many forms all at once. Others look to the genetic toolkit. Fossils may record bodies, but hidden inside those bodies were genes that told them how to grow. By the time of the Cambrian, organisms had unlocked the Hox genes, a set of genetic switches that could be rearranged to create new body plans. This toolkit may have been like handing evolution a box of paints after working for billions of years with only a few colors, yet even here there are mysteries. The genes themselves may have existed earlier, so why did they suddenly unleash such dramatic variety in this particular era? Predation is another piece of the puzzle. Once one animal developed the ability to actively hunt, every other creature had to adapt or perish. This arms race, with predators growing sharper and prey growing tougher, could have driven the rapid spread of new strategies, from armor to speed to camouflage. But this idea, too, leaves questions unanswered, because it does not fully explain why predation itself began to flourish just then, and not long before or after. The fossil record complicates the story even more. Molecular clocks, which use DNA to measure when lineages split, sometimes suggest that the ancestors of many Cambrian animals existed well before their fossils appear. If that is true, then the explosion was less of a sudden spark and more of a moment when conditions finally allowed these hidden lineages to bloom into visibility. But if so, why do the rocks remain silent until that point, preserving so little of the life that must have been there? There are also questions about the environment itself. The Cambrian was a world of shifting continents, shallow seas, and changing climates. Plate tectonics may have created vast new habitats, each one a cradle of innovation. Shifts in nutrients, stirred up by erosion and the movements of the seafloor, may have sparked blooms of algae that fed expanding food webs. But teasing apart cause and effect is difficult. Did new environments drive the explosion, or did the explosion itself reshape the environments? Even the word explosion is debated. To a geologist, it describes an interval of perhaps 20 million years, which is long compared to human time, but short compared to the billions of years that came before. Was it really a single event, or a series of pulses, with bursts of innovation separated by quieter stretches? Some scientists even suggest that the explosion is partly an illusion, amplified by the sudden appearance of skeletons that fossilize well, making the Cambrian seem richer in diversity than the ages before it. Yet despite these uncertainties, the Cambrian explosion continues to captivate because it represents a threshold. It was the moment when life crossed from the invisible into the visible, from simple forms into elaborate creatures with limbs, shells, eyes, and teeth. It was the moment when ecosystems became tangled and dynamic, when survival depended not just on chance, but on competition, adaptation, and innovation. And though the exact triggers remain uncertain, the outcome is clear. The foundations of the living world today were laid in those ancient seas. The questions that remain are not failures of science, but part of its beauty. Every fossil uncovered, every genetic study, every new clue adds detail to the picture, but also opens new doors of wonder. The Cambrian reminds us that even the most dramatic events in Earth's history can resist simple answers. It is a reminder that the story of life is not a straight line, but a web of mysteries, some of which may never be fully solved. 500 million years ago, Earth's oceans were filled with beings that seem more like visitors from a dream than ancestors of the world we know. Worms with spines jutting from their backs, hunters with 5 eyes, creatures with mouths like circular saws, all moving across the soft mud of shallow seas. They look alien to us, yet they are not strangers. In their strange bodies were the beginnings of the patterns we still carry today. The eyes that open to the Cambrian light are echoed in our own. The muscles that first pulled bodies across the seabed still stretch and contract in us. The nerves that fired inside their fragile forms have become the thoughts moving inside our minds. It is a humbling thought that our story began here, not as people, not even as mammals or fish, but as tiny, experimental shapes in a restless sea. Our ancestors were once spined and soft, exposed to predators, caught in the endless dance of survival. They were fragile, but they endured. From them came the slow unfolding of every lineage that fills the planet now, from dragonflies that glitter in summer air to whales that dive into the deep, to human beings who look back and wonder at the mystery of where it all began. The Cambrian explosion was not simply an event in prehistory. It was life's first great experiment in complexity. It was the moment when nature opened the doors of possibility and allowed the imagination of evolution to run wild. Most of what was tried did not last. Whole body plans disappeared forever, leaving only faint impressions in stone. Yet out of that great wave of trial and error came the foundations of what we know as the living world. The tree of life branched upward, and one of those branches is us. There is something delicate in remembering that it could have been otherwise. If oxygen levels had not risen, if seas had not grown shallow, if genes had not unlocked their hidden toolkits, the ocean might have remained a quiet place of drifting microbes and simple forms. There might never have been eyes to see, or hands to write, or minds to question their own origins. The Cambrian reminds us of how finely balanced our existence is, built on thresholds that were crossed by chance and necessity working together. When we look at the fossils, at the fine ridges of a trilobite's eye, at the delicate outline of an Opabinia's trunk, we are not just studying extinct creatures. We are seeing ourselves in a distant mirror, one polished by stone and time. These were not merely oddities locked away in ancient seas. They were the first drafts of us, the earliest attempts at bodies that would one day think, feel, and reach for the stars. And so the Cambrian explosion is not only the story of alien seas and strange monsters, it is the story of us. We are the living echoes of that ancient experiment. The blueprint that was first drawn in those shallow oceans has been carried forward, reshaped and refined, but never erased. In every breath we take, in every beat of our hearts, in every step we walk, there is a quiet whisper of that half-billion-year-old dawn. Life is fragile, and yet it endures. From the spined worms and armored crawlers of the Cambrian to the vast variety of beings that walk, swim, and fly today, the thread of existence has never broken. It has only changed shape, finding new ways to survive, to grow, and to explore. As the story of the Cambrian closes, it does not end. Its echoes remain, not just in rocks or in fossils, but in us. The seas of that long-ago world are still inside our blood, which carries salts much like the ancient oceans. The genes that guided those alien creatures are still guiding us. The wonder they began is still unfolding. So when we think of the Cambrian explosion, we are not simply looking back at a vanished world. We are remembering the moment life's great story truly began. The story of the Cambrian is the story of us, and even now, in the quiet of the present, we are living echoes of that first great experiment.